All right, let's take a look at problem 5, which is a shorter problem, but just intended to get you to think a little bit. So the following data are available for a gas. All right, so let me emphasize for a gas. To calculate the molar volume at 25 degrees C and 12 bars, all right, so we have data at 25 degrees C. Both data points are 25 degrees C. One's at 0.5 and one's at 0.15. So pressure is between the two. Your team came up with two different suggestions. A, linear interpolation for V between the given pressures. So linear interpolation using this data. Or linear interpolation for the density, where the density is 1 over V. All right, so the alternative would be to compute density, which is 1 over V, and then interpolate in density with respect to pressure. Okay. Under what conditions is your recommendation accurate? And so this is just a problem to try and get you to think about interpolation a little bit. Now I know when we go to the steam tables and we interpolate, oftentimes we're just interpolating. We're not bringing in any of this insight, or else we should have in problem 4. But just to give you something to think about. So the idea is if I consider the case of an ideal gas. Okay. For an ideal gas, right, I know I have my ideal gas equation of state, which tells me that PV is equal to RT. Okay. So now R is my molar gas constant, and then T is temperature, which in this case is being held constant at 25 degrees C. Right. So RT is in theory just constant. Okay. So therefore PV is constant. So the key is, right, for my ideal gas, is that my pressure is proportional to 1 over V, right, which is equivalent to my density. So pressure scales, right, is proportional to density, right, whereas pressure is inversely proportional to specific volume. And so just based on, the scaling that we'd expect from the ideal gas equation of state, right, scenario B would be suggested to be the better approach to interpolate with respect to density. All right, so based on ideal gas equation state and how we would expect pressure to scale with respect to V, we would expect linear interpolation to be better if we were to interpolate with respect to the inverse of volume. All right, and under what conditions is this accurate? So this is assuming we have an ideal gas. Okay, if we were to think in general, our equation of state for real fluids, right, takes the form of PV equals ZRT. Okay, so Z we expect to change with respect to P, right? Z is going to be a function of both, T and P. But if we assume that, that change in Z is small, right, then, we'd still expect similar scaling. Okay, so hopefully that helps. The purpose of this exercise is just to give you, something to think about. If we could bring in some physical insight to when we perform these interpolations, right, we'd expect the results to be better.